This lesson has been developed in the framework of SCILED project. Module 1, Footwear Performance and Comfort. Unit 2, Mechanical Comfort and Footwear Performance.
Lesson 2.1. Human Foot and Gait Cycle. This lesson is structured as following.
Foot anatomy, bones, joints, arches, muscles, ligaments and tendons, foot movements, foot troubles, variation in feet, gait biomechanics, static conditions, phases of normal walking, gait parameters, kinetic parameters, force, pressure, center of gravity and center of mass.
Foot anatomy.
Before designing and developing the footwear product, is helpful to understand the human feet, in order to offering to the consumer a product which will meet his or her needs regarding fit and comfort. The structure of the foot is a unique masterpiece of architecture, or rather of biomechanics, comprising bones, joints, muscles, tendons, ligaments, veins, arteries, capillaries, nerves, and other tissues. The foot bones are divided into 3 parts.
Hindfoot, ankle bone, A. Heel bone, H. Navicular bone, N. Cuboid bone, C. 3 cuneiform bones, C1, C2, C3, midfoot. 5 metatarsal bones, M1, M2, M3, M4, M5. Forefoot, 14 toe bones, 2 sesamoid bones.
The foot and ankle complex involve numerous joints which have been hypothesized to fulfill a significant role in the lower limb kinetic chain during human locomotion. Similar to the bones, the joints are divided in 3 groups: hindfoot joints, midfoot joints and forefoot joints. The arches of the foot, formed by the tarsal and metatarsal bones, strengthened by ligaments and tendons, allow the foot to support the weight of the body in the correct posture with the least weight and ensure stability and flexibility. The muscles in the lower segment of the skeleton support the control of the foot, and they have 3 primary functions: to stabilize, to accelerate, and to decelerate. All 3 functions must happen during normal gait. The function of the muscles of the foot is coordinated by numerous tendons connecting the muscles to the bones. These tendons begin in the lower leg and descend to the foot, where they assist in the movement of the toes, and they can't be controlled actively.
Foot movements. Motion includes movement of organs, joints, limbs, and specific sections of the body. Dorsiflexion is the backward flexion or bending of the foot. Plantar flexion is the extension of the ankle so that the foot points down and away from the leg. Pronation and supination are normal motions of the foot during the gait cycle, walking cycle, and are terms of motion usually applied to the subtalar joint. Inversion and eversion are passive motions which refer to movements that tilt the sole of the foot away from eversion, or towards inversion, the midline of the body. Toe movement. The short foot muscles control the movements of the toes and make possible to do the following motions: bending, stretching, spreading. Foot troubles. Variation in feet.
Even in healthy feet, there are many differences between the people's feet shape, which could be influenced by individual factors, such as gender, demographic data and habits. Hence, the fitting of the shoe will be influenced. According to Miller, foot troubles could be divided in 4 categories.
Damage to the skin, troubles of the toes, troubles of the arches, valgus ankle and pronation.
Many foot troubles are associated with specific foot types, which could be evaluated using visual assessment, footprint parameters and anthropometric values. Some research identifies different foot types in accordance with the alignment and arch height: planus, flat, rectus, well-aligned, or cavus, high-arched.
Gait biomechanics.
Biomechanics studies provide information that will lead to the determination of the rational shape of the insole, the shape and size of the heel, its strength, as well as other information regarding the requirements of the other component of the footwear. Mechanics, which is the science of movements and the forces acting thereby, includes not only the sole description of human movement, kinematics, but also the forces that cause those movements, dynamics. Kinematics describes the motion without analyzing the reasons for the motion. Dynamics focuses on why there is a movement. Dynamics could be divided into statics and kinetics, depending on if there is a balance or imbalance of the forces.
Static condition.
The standing posture is important for human motor abilities, and to leading the controls of it is a vital requirement for daily physical activities in life. In the orthostatic position, the human bearing surface is determined by the size of the plantar surface of the two legs that are in contact with the ground. As it is shown in the figure, the projection of the center of gravity of the body is located at point O, placed between the two planting surfaces and slightly moved to the right of the axis of symmetry. In a standing position, the body mass is equally distributed over both lower limbs. The pressure determined by the weight of the body is transmitted through the tibia to the astragal, and through it a part of the loads is distributed on the calcaneus and another part on the scaphoid and cuboid to the heads of the metatarsals 1 and 5. During standing, kinematic parameters, such as the angles of joints, 1t change that much. In case of the average angle of the upper ankle joint, we can note that while barefoot standing the angle is 112 degrees, and it increases to 115 degrees or 137 degrees with leisure shoes or high heels.
Phases of normal walking.
The gait cycle has been divided into 8 stages, 5 for stance and 3 for swing. The main stages that will be detected during the stance phase are: initial contact. This phase includes the moment when the leg starts contacting the ground and the ground reaction force appears only at the heel level. The joint postures present at this time determine the limb's loading response pattern. This stage takes about 15% of gait cycle. Loading response, time period from immediately following initial contact to the lift of the contralateral extremity from the ground, during which weight is transferred onto the forward limb. Using the heel as a rocker, the knee is flexed for shock absorption. Ankle plantar flexion limits the heel rocker by forefoot contact with the floor. The opposite limb, clear, is in its pre-swing phase. Midstance, when both the forefoot and heel start contacting the ground. In the first half of single limb support, the limb advances over the stationary foot by ankle dorsiflexion, ankle rocker, while the knee and hip extend. The opposite limb is advancing in its mid-swing phase. The mid-stance phase starts and lasts from 15 to 30% of gait cycle. Terminal stance, as the center of body mass moves forward in the terminal stance phase, the heel starts taking off. In this phase, only the forefoot part touches the ground. The knee increases its extension and then just begins to flex slightly. This stage continues from 30 to 45% of gait cycle. Press-swing, time interval from initial contact of the contralateral extremity to just prior the lift of the ipsilateral extremity from the ground, unloading weight, which takes about other 15% of gait cycle. This phase is also known as weight release and weight transfer phase.
The hypothetical normal foot position during the stance phase occurs when
no forces are on the foot from the leg in any of the 3 body planes. The heel bone is in line with the leg and perpendicular to the ground. The plane of the forefoot is perpendicular to the rear foot and parallel to the ground. The ankle joint can dorsiflex 10 degrees.
Gait parameters. The most commonly reported measurements of gait are the temporospatial parameters. Some of them are walking speed, stride time, stride length, step length, step width, cadence, stance time, swing time, foot rotation and cycle time. Step time is the time needed for one step or stride between the contact points of the right and left feet. Step length is the distance between the position, for example, heel contact, of one foot in the next similar position of the opposite foot. In other words, is the distance between the contact points of the right and left feet. Kinetic parameters.
The main kinetic parameters which characterize the foot biomechanics during walking are force, pressure and center of pressure. The force, F, is described with the mass, m, of an object and with the acceleration, a, of that object. In short, F equals ma. The most common exterior force applied to the human body during walking is the ground reaction force. This force is a 3-dimensional vector comprising a vertical component and 2 shear components. In heel strike, the human foot, h, contacts the ground and exerts 2 elements of force in forward, hx, and downward, hy, directions into the ground. The ground reacts with the same amount of force in the opposite direction, gx, gy, to the foot. Another force acting during the walking is the frictional force, which acts in the opposite direction to the horizontal component of the force of the foot on the ground in order to prevent the slipping action. The pressure is the force applied perpendicular to the surface of an object per unit area over which that force is distributed. In the stance phase, the highest pressure is moved predominantly from the heel region to the toes. Some studies demonstrated that the angular displacement of the hind and midfoot, especially at the second peak instant, clearly changed. The angle between the ground and the axis along the first ray in the normal foot is 28 degrees. At the same boundary condition, the foot shank angle was 30 degrees from the vertical direction.
Pressure distribution changes when wearing footwear. An appropriate shoe, and especially bottom assembly, contributes greatly to the pressure distribution on the plantar surface of the foot. Shoes with flexible sole decrease plantar pressure and contribute to the foot proper shape and function.
Walking and gait cycle could be considered as a pendulum and could be seen in the left figure. During the gait cycle, the body's center of gravity increases and falls over a stiff, supporting leg, creating an exchange of kinetic and potential energy. The second figure shows the center of mass, M, location and reaction forces, F, applied at the center of pressure during a double support period. According to this research, the bipedal inverted pendulum model suggests that the angle between center of mass and the center of pressure determine the magnitude of the required coefficient of friction during straight walking.